Okay, so can you hear me?
We can hear you.
Okay, thank
Yes,
you.
yes, yes.
Okay, great. Good afternoon to every single one of you. This time, I'm not using my headset because I'm in Corfu. I'm in the laboratory, so if anyone is in Corfu right now, you can basically meet me after today's lesson. Today we are going to start with pretty much a practical example of everything we've seen over the course of the past 5 days that we've been together. So it's actually this course that we're going to run through today is basically all the steps that we've already seen and a few additional ones. But this time we're actually going to employ them on a real data set, like a real clinical data set to be exact, like a biomedical problem. And in the next lecture at the 17th of the month, we are also going to check out some more complex deep learning architectures for specific biomedical problems. But let's start with today's example. So today's data set, the data set that we will be using today, can be found through this link right there. It's the heart disease data set. Let me also um, share it with you here in the chat. I'm also guessing that you can see my screen. Is that correct? Could anyone please
Yes,
confirm?
yes, it's correct.
Yes.
Okay, great, thank you. Today's data set has actually been created by three, or rather four clinics right there, as you can see. This is the UCI repository. It's actually an online website, or rather a large database full of different data sets. And you can actually check it out if you want to. There are many different things to choose from, but we're going to go with this one for now. It's a fairly small data set. As you can see right there, it has 303 samples or instances and about 13 features, 14 if we also count the target variable. The associated task, as you can see right there from the page itself, is classification. I'm also going to add to this that the task that is associated with it is multi-class classification, which means that by default, we have to either classify a person as either healthy control, someone that is not really suffering from cardiovascular disease, or as someone that suffers from the disease, and basically classify the specific stage of the disease, like how severe is the disease stage for the person, for the particular sample in our data set. So how can we actually use this particular data? I mean, how can we download it? How can we import it in Python, as we've seen? Oh, is there a question in the chat? Oh, a thumbs up. So thank you. So how can we actually, start using this data set? Well, one thing we could do is basically go over there and download it. But the problem is that it's actually in a very common format, at least when it comes to the data sets in the UCI repository. In most cases, through this specific repository, is that you have data sets in the form of databases, which means that you're not really using a CSV or an Excel file. So is there an alternative that we can actually use? And the answer to that is yes, there is. We could actually go on here and press this import in Python. And this is basically what we're going to do. So the first thing that you got to do is basically install this package, which we have already done through our V&V process that we've seen over the course of the past days. And then you can basically copy this code in your own notebook and basically import the data set, which means import the matrix, the data frame, as well as the target variable. I'm also seeing that there is a question in chat, perhaps. Oh, maybe I'm actually seeing a notification, but it must have been from before. So another point of change here that you can possibly check is that this time we're using Jupyter Notebooks, but instead of using it through Jupyter itself, like we've been doing the days, we're actually using it through Visual Studio Code. And the reason why we've actually made this change that so that it can become apparent and clear to everyone that just because we've been using Jupyter notebooks through Jupyter itself does not mean that we cannot use them through an editor, a code editor like Visual Studio Code right there, which is the one that I personally prefer. The only thing that you will always have to make sure, however, especially when you're working with VS Code, is to actually use the VNV that you've created, or in other words, the Python kernel where every library is going to be installed for your project. And as you can see right there, it's this tab right on the top right part of the notebook. So if I actually wanted to use a different environment, I would go on there. I would go on to select another kernel and basically move on with the kernel that I've basically chosen. It could have been something like Python 3.12 or 3.11, according to the project, of course, that I'm always running. So having said all that, let's actually start working on our data. So the first thing that we got to do is start, pre-processing our data. This is actually something that we haven't really seen before in the case of Iris, because when we were working with Iris, what happened was a data set that was already cleaned to begin with. It was a benchmark data set. This one that we're working with here today is actually a bit different, and we are going to run through, some initial steps that we have to undergo in order to bring it up to spec when it comes to moving on with exploratory analysis and classification and clustering and so on and so forth. So the basic strategy that we're following is basically the same as we've done with our previous notebooks, as we've seen over the past days that we've been talking together. So the first thing that we got to do is actually start importing the necessary libraries or packages. You can call them whatever you want. I remind you that in order to do so, you have to click into the code cell and then press Shift Enter. And as you can see, the code cell run. The second thing that we need to do is start initializing our homemade functions. That is, code that we've actually written so that we can perform, certain tasks by ourselves or automating specific processes. You can see here that we are initializing a homemade function, and we're going to analyze what it's actually doing a bit later. And then we actually have to import our data set. So through this code right there, what we're actually doing is that we're making a connection with UCI repository, and we are asking it to fetch data set with ID number 45, which is the heart failure data set that we've described previously. So we run this code. It might be a bit late for some people because depending on different connection speeds. And once we do so, we need to do two things. So if you actually use this heart disease object, we can also check it out there. So let's use it to basically see what's going on. You can see that we actually have our features, our input features, our data frame in a format that is not really all that great. I mean, it's essentially a dictionary, but it's not really all that intuitive when it comes to using it for either pre-processing or exploratory analysis, visualizations, and so on and so forth. So we need to extract the pieces of information that exist within this object into a matrix, which is going to serve as our data frame, as well as a matrix, which is going to serve, or rather a vector, which is going to serve as our target variable. And this is basically what we're doing with these pieces of code right there. And what you're actually going to see is that if I run this code after basically being able to isolate my data frame, is that this is exactly what I get. This is a pandas data frame with all of my input features. So once again, what is a data frame? It's basically a very tidy version of a matrix, which actually helps us understand the way our data are structured. So our rows are basically samples or instances. These are our patients in our case, and our columns are actually our features, or rather, in our case, because we are talking about clinical data, the different measurements that we have for our individual patients. And you can also see that we have 303 rows, or patients, once again, as well as 13 columns, which is our measurements. I'm just, reminding you of what we've seen so far with previous data as well. And if I go on and execute this code cell, well, that was a bit of a spoiler, but you're actually going to see here that this is our target variable. And we have many different values. We have 1, we have 0, we have 2, we have 3. So basically, we are dealing because we already know that it's categorical, we've already seen the description online, that we're dealing with a multi-class problem. And this is basically a problem, so to speak, or rather an issue that we need to tackle before we move on. And the problem is, are we actually going to start by approaching the classification task that we want to run at the end of the day as a multi-class problem to begin with, or are we actually going to try and simplify it? And how can we actually simplify it? We can basically move on and transform it into a binary classification task, where instead of actually using 4 different values for our target variable, which would correspond to healthy controls, as well as the many different stages of a disease, we can actually transform it into either 0 or 1, which will correspond for controls, for 0, or rather healthy people, and 1 for people that are actually suffering from cardiovascular disease. Before doing that, however, we can also use our value counts in order to check out the distribution of our different patients. So you can basically check right there that we have 164 people belonging into category 0 or healthy controls. And then we have these many people right there in our other 4 different categories. So one of the very first things that we would actually say about this particular data set is that if we actually use it as a multi-class problem, if we use it as is, that is, it's actually a fairly imbalanced data set, because we have 13 people in category 4. We have 35 here in category 3. These are different levels of severity for cardiovascular disease, once again. And then we have these many people in category 0. In other words, at least when it comes to category 4, the number of people of that category is actually at least 2 times, to say the least, that is, compared to category 0. And this can actually create problems when it comes to training and evaluating our algorithms. It can actually introduce bias and thus lead to false results down the line, as we've already said before. So the first thing that we need to do, again, before moving forward with cleaning the data set further, is actually start with our initial narrative, and that is basically through simplification. So once again, we are going to turn our multi-class classification problem into a binary, at least for now. Does that mean that we will always have to do so? Does that mean that if we start with a multi-class problem, we will always have to turn it into a binary classification one? Well, that actually depends on the requirements of every project. So this is kind of a diplomatic response, but if there is no specific requirement set out by the doctors or the biologists of the team, at least when it comes to biomedical problems, we could actually try both, which means that we would start with the simplest of approaches, that is a binary problem. And then if we actually see that it doesn't really work after trying many different techniques, many different methods of preprocessing and whatnot, we can actually go back to the drawing board and start anew by approaching it as a multi-class problem, or rather in its default initial setting. So having said all that, how can we actually transform our problem into a binary classification one? Well, as we've seen before, what we're actually going to be using is a mapping. So we're going to be using a dictionary. You can see here that 0 remains 0, of course, 1 remains 1. And then these other 3 categories of severity, or levels of severity rather, are actually going to be changed to 1. So the question that I'm asking, essentially, is not whether a person is a healthy control or whether he belongs into different levels of severity. I'm keeping it simpler, and I'm asking essentially whether a person is either a patient or rather suffers from disease or not. And since we've actually done this conversion, if I go on and check the value counts, I'm actually getting this kind of picture. So I'm getting 164 people in category 0, just as it's been before. And then I'm getting about 139 people in category 1, or in other words, 139 cases. And this actually looks a much better, it's actually a much better picture or data set, because right now we could actually say that this particular representation of our data means that we are working with something that is balanced and thus has greater possibility of giving us a final objective, good result when it comes to predictions, that is. And then, of course, we can also check the tag, which now has values of 0 and 1, as you can see right there. So the next thing that we have to do, since we've already simplified our task, is to be able to check whether there are missing values in our data set. Let's do just that. So as you can see here, this is a piece of code that we use to determine which columns have missing values, which means which features include values that are missing, or rather do not include specific values, that is. And then we can also check the specific samples or rows that have or suffer from missing values. So missing values actually look like this, the NaN right there. So what does that mean for us? It basically means that these particular samples that you see here do not have specific values for these particular features. Now, why is that the case? It could have actually been many different reasons. It could be just because of the fact that these people did not undergo the necessary examinations to have this kind of information extracted out of them. In a scenario where we're using questionnaires, it could be that these people did not really want to answer to these particular questions, and so on and so forth. So there can be many different reasons, but at the end of the day, we do not really care about what the reason behind the existence of the missing value is. What we care about is actually dealing with it, actually tackling it. So there are many different ways of using, or rather working with, missing values, the simplest of which is basically either discarding the samples that contain missing values, or the features or the columns that contain them. So when should we actually do each of which? So if you actually have, a row or a sample that includes many different missing values for the majority of our features, then it would be best to just, discard it entirely from the data set. However, if we have a feature that has NaN values or missing values for about like 60 or 70% of our rows, then this basically means to us that this particular feature is not really meaningful, or that it's not really helping us understand what's going on in the data set, because we simply do not have that kind of information. So in that particular case, we would actually have to discard the feature or remove it. There is also a third, kind of approach in all of this. You could also go with data imputation, which is a series of techniques that can be used for this. So what happens with imputation is that instead of actually removing either rows or columns, you're trying to replace these NaNs, these missing values, with synthetic ones, so to speak. And the most traditional thing to do, or the most straightforward, I'd say, is to actually use algorithms that are based on the KNN classifier, and basically find, for example, for this particular sample, which are its k nearest neighbors. And you're going to determine this by looking at the other existing values for this particular data set. And then basically take the values of the k nearest neighbors for this particular feature and calculate either the mean or the median or some other kind of statistic, and then replace the NaN value with this particular statistic. Is this the correct way to go when it comes to biomedical problems in particular? Well, it's something that we could definitely do, but it's basically kind of a double-edged sword, because in most cases, doctors and biologists do not really want to do this. And the reason behind this is because by introducing synthetic values, so to speak, you're not actually, helping them out. You're essentially trying to avoid the problem by providing information that might not be true at the end of the day. So in these particular cases, at least when it comes to biomedical problems, the most well-established way to go, or at least the one that is encouraged in most cases, is to either discard of samples or features. But then again, it also depends, because even if a sample or a particular feature has a lot of NaNs, a lot of missing values, it might be important because it might actually give out some kind of information, maybe because it's an outlier and we want to see how it interacts with the other samples or features, depending on what we're talking about in the data set. So in our particular case, for this example, what we are going to do is actually discard our samples. And The reason why we are discarding samples, again, is because discarding things is actually the established way to go, at least when it comes to biomedical problems. The second reason is because, as you can see right there, we actually have very few samples or rows that have missing values for these particular features, which means that these two columns actually have real values for these two measurements. So it's actually an easier and perhaps a better thing to do rather than discarding of these two measurements. So you can basically do this by using this piece of code right there, and the end result is going to be this. So in this code, we're actually doing two things. The first one is to essentially add the tag column in our data set. So we're also including the target variable, which was not available before. As you can see here at the top, I'm going a bit behind. So it's not included there. So we wanted to have this as well so that we can have a single concise object to work with. And the second thing that we're doing through drop NA is basically removing these particular column or rows right there. So right now we have a data set that includes 297 rows and 14 columns, right? So we've actually managed to download our data set. We've managed to simplify our problem into a binary classification one because this is what we wanted to start out with. And then we've also removed missing values. So before moving forward, the one thing that we could do, because just as a reminder, we don't have an Excel file or a CSV file. We've basically fetched a data set from an online repository. So the one thing that we could do is actually save this data set in memory as a CSV file. And this is something that can be done through, the code like the one that you see here. So are these the only pre-processing steps that we can undertake when it comes to working with our data? No. So let's see what else we can actually do. So one thing that we could do, for example, is look at a specific, measurement like cholesterol, for example, right there, and transform this into a categorical variable. So why would we actually want to do this? And the reason behind this is because in some cases, having continuous variables with many different values is not going to be helpful either for us or for the medical expert that we are collaborating with. So in some cases, they might actually want us to use a certain threshold through which we will be able to determine whether a person is actually healthy or not, so in relation to our tag, or rather whether this particular person has a high risk or a low risk of being, a patient or suffering from disease. So this is basically what we're trying to do with the convert to categorical function that you've seen up top, the one that we've created ourselves. So what it actually does, so the inputs for this function is a data frame. You also have a particular column name that you wish to convert. And then you also have a threshold value. Now, the thresholds can actually be determined by many different ways. So the first one would be to experiment with many different values and combine what we've seen empirically with the available literature. So reading a lot of papers. And the second thing to do is, for the most well-established thing to do, I'd say, is actually consult the biomedical expert that we're collaborating with. So in most cases, the threshold is predetermined by the doctor or the biologist that we're working with. So what we're actually doing, having all these information at hand, is we're actually checking to see whether this particular column exists within our data frame. If it does not exist, we raise an error, of course, so that we can actually let the user know that it does not. But if it does, we are actually converting it or converting its values from numerical, as you can see here from this if statement, basically, into a categorical one. So if the threshold is passed, you're actually going to say that this person is normal, or rather that the risk is low. And if it's not, then the person is at risk. Okay. So this is basically what we're going to check out now. So let me move further down. So, and as you can see, this is simple as that. So you basically give the data frame, the column name, which is cholesterol, this one right there, and then a particular, threshold value. And if you run this and then you move on, you can basically check that cholesterol is now risk and normal. So we've basically replaced the continuous variables or the continuous values that you have with these categorical. So we basically turned it into another categorical, binary kind of variable. So does that mean that it's over? Like this is the only thing that we need to do for this particular column or cholesterol in our case? No, we would actually have to basically move on with some sort of conversion. So we would have to basically convert it into zeros and ones so that our models or the algorithms that we're going to use later on down the line can understand that this particular column is actually a binary categorical variable. Because once again, if you give risk and normal as input to a particular algorithm, like a machine learning algorithm, a classifier that is, or even for unsupervised learning, for clustering, we are not really going to understand, so to speak, what we're trying to relay to them. So this is the reason why we need to make the conversion. I'm just reminding it. So another piece of pre-processing that we could do is bin our ages. What does that mean for us? So you can see here that we have, specific particular values for ages. And perhaps you can see this in a clearer way, a more intuitive way that is here through this column. So in some cases, you might not really want to have something like this. You might want to convert this again into a categorical variable. So I might want to classify people that are 63-year-olds, as belonging to the senior category, for example. So how would I actually proceed to do this when it comes to ages? So I would actually create bins, or what that means for us is that I would actually create specific, groups of people through which I would be able to classify or basically put the particular samples of our data set depending on these unique values that we see here. So one group would be from 0 all the way out to 30 years of age. The second group would be from 31 years of age all the way out to 60. And then the other one would be from 61 all the way out to 80. So we basically have three particular groups, which are then going to be converted into young, middle-aged, and senior. Again, does that mean that this is something that we will always have to do when working with data sets such as these? Does that mean that we will always have to convert our ages, for example, or variables like cholesterol, for instance? No, not at all. I mean, this again depends on the narrative. However, binning for ages is actually a pretty well established technique. It's optional in most cases, but if algorithms do not work all that well on our data, one thing that we could try to do when it comes to pre-processing is come back and basically start modifying the values of our features, age included. So if we wanted to do this, this is basically the approach that we would go on with, basically binning and then converting to specific particular categorical groups. And then, of course, we would have to convert both of these columns from categorical and textual into categorical and numerical. So we would do this once again through the use of dictionaries, as you can see, right there. So we initialize our dictionaries, and then, of course, once again, we use them in order to be able to create our categorical variables, in this case, age and cholesterol. So these are some of the basic initial steps of pre-processing that we can apply on our data set. So before moving on with visualizations and the rest of the insights that we're going to check, are there any particular questions on this part when it comes to pre-processing? Something that you would perhaps like to discuss, something that you'd like to ask, anything at all? You can also use the chat if you don't want to open your microphone. Okay, so let me reiterate. Was everything understandable up until this point? Is everything clear? Okay, I suppose it was. So let's move forward with the next part of our data analysis or for analytical process. So the second thing that we need to do is basically, oh, you're welcome. Okay, so thank you for the confirmation. So the second thing that we need to do is basically start visualizing the patterns that are available within our data set. So you do remember that we actually have things like box plots and PCA plots and whatnot. So this is what we're going to check out now. We're also going to check a few more plots. So let's go on and see, what's going on for our particular case. So the strategy that we're following, once again, for the second notebook is pretty much the same as we followed before. So we import the necessary functions. So cancel that. We don't need that for now. And then we basically initialize our mappings or our homemade functions. And then we can basically read, our data set, which is now stored in a CSV file in that case. And you can see right there, so that you can also see that for this particular example, the second part of our pipeline, we're using the data set as it was basically after removing missing values or the rows that contain missing values. So for this particular case, we will continue by using age as a numerical feature, and same goes for cholesterol. Could we actually use the other version of our data set, like the one in which we actually modified age and cholesterol? Sure, we could, but let's move on with this one for now. I mean, this is something that you could try out yourselves if you want to. These materials are, I think, already available for you, so it would actually be an interesting experiment. So as you can remember from before, we've actually used value counts in order to be able to check the number of samples for the two categories that we're working with. And we can actually visualize that piece of information by using bar plots. So what we basically see here, once again, is pretty much the same kind of information that we've seen before. But right now, it's much more intuitive. It's much better than having sort of a small matrix with two numbers. So what we see here, once again, is that we have 160 people belonging to the control group, or rather people that are healthy. And then we have 137 people belonging into the case category, which means that these 137 people are actually suffering from cardiovascular disease. So what that means for us is that this particular data set, again, is actually fairly balanced. It's actually very, very good in terms of balance. It's, I'd say, a fairly ideal case because in a lot of biomedical problems, what they actually do suffer from, as we've seen before in the multi-class instance of this particular one, is having minorities when it comes to different groups. So moving forward, we can actually perform data standardization or normalization, as we've seen in our previous lectures. So again, just as a reminder, this is a melted data frame, by the way. So just as a reminder, if you actually go on and standardize or use z-scoring for normalization of your data, you're actually going to get both positive and negative values, as you can see right there. Just because we have negative values for particular features like age, for instance, does not mean that you actually have a negative age. It actually means, this particular one, for example, that this sample or this person has an age which is 1.94 times lower compared to the average age or the mean of the age of our data set. It could also be called in a statistical manner that this person has 1.94 standard deviations lower when it comes to age compared to the mean. And pretty much the same case applies for our positive cases right there. So this particular sample, just to make this 100% clear, actually has an age which is like 1.17 times bigger, whatever you want to call it, compared to the average, or rather the TAL, because this is a different feature. It's not the age, but you get the idea. Now, why did we actually create this particular version of our data set? I mean, this looks really intuitive, right? It actually looks fairly good. So why did we go on and switch onto something like this? it's not really helpful for us now, is it? So the reason behind this is because this is the input that is required for violin plots, which is basically what you see here. So what these plots actually show us, and you can see that I have many different violin plots, each of which corresponds to a specific feature or measurement of our data set. So what each of these actually show us is the distribution of values for the two different tag values that we have. So it basically shows us how our values are actually distributed for our two different conditions. That is for controls, as you can see from this color and the color coding right there, as well as cases. So why would we actually want to use a plot such as these? Well, the answer to that is because if these two sort of mountains, let's say, so to speak, are actually completely symmetrical with each other, for example, like in the case of this particular feature, then this basically means that this particular feature has no real difference when it comes to its values for our two conditions. So it might be that this particular feature is not really helpful when it comes to making meaningful, precise, accurate predictions. However, if we actually check out differences in terms of distributions, for example, for tall, for CA, you can see that they're not symmetrical with each other, the two mountains, so to speak, once again. So this can actually mean that we have a specific set of distinct values for two conditions. They actually differ between conditions, that is. And for that reason, I would actually expect that later on down the line, these features are actually going to be important when it comes to distinguishing between health and disease. And this can be made even more concrete if we employ the help of something like this. This is a correlation heat map. So again, we are using Pearson correlation, which gets values from -1 all the way out to +1. So a value of -1 would actually indicate an absolute negative correlation between samples, which mean between features, sorry. So what that means for us is that when the value of one feature, gets greater, then the value of the other feature that we are actually having in the pair will get lower. So this is the absolute negative, correlation, or -1. An absolute positive correlation, which is going to be +1, actually indicates that if the value of a particular feature gets greater, then the same pretty much happens for the value of the other feature that we're comparing it against. So in other words, if we to put things into a bit of a more concrete sense, we actually have the tag here. This is our target variable. And we basically go on to tall. This is another feature that we have. And we see that these two particular features, these two particular columns, actually have a fairly high positive correlation. What does that mean for us? It actually means that as the value of tall rises, as it gets greater, the same thing happens with the value for tag. However, you might be thinking now, but wait, our tag actually has, two values like 0 and 1, right? And that's the whole point here. So what that means for us is that while the value of tall rises, the same thing happens for tag, which means that it goes from 0 to 1. And this can basically mean in a biomedical context that this particular feature means that the higher the tau value, then the more likely it is that a particular person will be suffering from disease. Now, is this something that we can actually conclude by ourselves? Like, is it something that we can hand out to people through a publication? Well, that's not really the case. I mean, the reason why I say this is because although we have these kinds of insights and these kinds of results, we will always have to hand them out to doctors and biologists at the end of the day so that we can actually get good biomedical, true biomedical feedback, which will either confirm or not that what we are doing when it comes to data science actually makes, true biological or medical sense. So these are some other plots that we could be using. Another plot that I don't have the code right now to basically run together, but I can actually provide it for you if you want, is something like this. This thing right there. So these are box plots that actually showcase the values, the distribution of values for a particular feature. In our case, we're actually seeing the CA, which is part of our data set, of course, between controls and cases. And you can actually see, again, this little line is the median. It's not the mean. So what we see here is that we have completely different values, between our two conditions for this particular feature. So this is one thing. We have different distributions. However, the other thing, the difference between this and the other box plots that we've seen through Iris is that we also have this thing right there, these little stars at the top. So what do these actually show us? What do they represent? They actually show us that the difference that you're observing, the difference when it comes to value distributions, is actually statistically significant. So this actually plays a very important role because in some cases, even if we actually point out that there are differences in terms of value distributions, they might not be statistically significant. Like a few values might be different, but at the end of the day, it does not really matter when we look at the bigger picture. The fact that we're able to get results such as these, with statistical significance, that is, will actually paint a more concrete picture of what constitutes as a good, biomarker from the set of features that we have available. So what does that mean for us? So what do we use at the end? Are we going to use this particular plot right there, like a correlation heat map, or violin plots, for example, or these kinds of box plots by themselves? The answer to that is that in most cases, or ideally in all cases, we should basically combine all of them, like be able to use all the pieces of information and insights that all of these plots will provide for us. Now, is that always feasible? The answer to that is unfortunately no. And the reason behind this is because if you have a clinical data set with few features, as we have right now, because we have 13 features and basically 14 if you also count the target variable, there are a lot of other data sets out there, that biomedical data sets, that is, that actually have many more measurements or features to work with. They can have like 1,000 features, or if we move on to gene expression data, they can have like 20,000 features. And you can understand that when we are working with, that many measurements, it's actually impossible to work with, something like this. So in these particular cases, we would rely on things like dimensionality reduction. So before moving forward with dimensionality reduction, spoilers, is there anything you would like to ask at this point when it comes to either pre-processing, or when it comes to these particular visualizations that we've seen together? Is everything clear? Is there anything you'd like to discuss at all? Oh, so I'm actually checking the chat as well. Okay, so Andrea is actually typing something, so I'm going to wait for a question. Okay, is there anything in particular that is not all that clear, so that we can actually discuss it? Is there, or to reiterate, what is the part of it that actually is kind of confusion, perhaps, so that we can make it crystal clear, or rather, if you don't want to discuss it now, it's okay. I mean, you can always send a message later if that's something that you'd prefer.
Sorry, I'm just a little bit tired because I had today a big deadline. Sorry. So
Okay, it's okay.
Your explanation was very clear and great, like always. It is only my fault. Sorry.
Okay, thank you very much. So again, if there is anything you'd like to discuss, I mean, the materials are pretty much already available to you, but if there is anything you'd like to, discuss, if there's any particular kind of thing that actually interests you, or something that concerns you when it comes to the methods that we talk about, you can, always reach out. I've already given my email to everyone, so feel free to, open up a discussion with me anytime you want. And that goes for pretty much everyone, um, that is, here today with us. So let's move on with dimensionality reduction. So we've seen before that aside from being able to create visualizations for our samples, or rather our features, sorry, we need to actually visualize our samples. And the problem that we've had with things like Iris, as well as this particular data set, is the X and Y axis that we're going to use. And we've also said that this is basically the reason why we're using dimensionality reduction techniques, things like PCA, which is a linear algorithm, or things like TSNE and UMAP, which are nonlinear algorithms. The reason why we're using them, just so that we can reiterate, is so that we do not actually have to make that particular choice. In other words, what we actually want to do is create 2 or 3 new dimensions that are actually going to be either linear in the case of PCA or nonlinear in the case of TSNE and UMAP representations, or combinations, which would be a better term, of our initial features, of the 13 features that we start out with. And the reason why we do this, the reason why we use 2 or 3 dimensions or vectors in order to do so, is because these 2 or 3 vectors, depending on the visualization that you want to run, are actually very helpful when it comes to actually containing the majority of the variability of our data set, or the variance, that is. So at the end of the day, this is basically what we want to keep. We want to keep the amount of information which, statistically speaking, is represented through variance. So again, the strategy that we're working with is pretty much the same exact thing that we've been doing with Iris and the other notebooks. So we're initializing, our libraries. Of course, we're importing everything we want. We initialize our mappings or functions. In this particular case, we do not really have a specific particular function that we need to work with. And then we're basically importing our data set, and we're also changing something. So the first thing that we need to do is remove the tag from the data frame. So we need to have it as a separate, object. The second thing that we did is actually change 0 and 1 into case and control. And the reason why we've done this is that so that we can actually color the samples of our data in a meaningful way, because, working with zeros and ones might be familiar to computer scientists and programmers, but it's actually very counterintuitive when it comes to working with, doctors and biologists, and rightfully so. So it's actually a better thing to use a representation or an encoding such as this one right there, cases and controls. So just as we've done before, we're going to run our PCA. You see that once again, we have the data frame that we have with our principal components, as well as the target variable. However, what we get here is actually quite different than what we got when we were using Iris. And I personally say, as a data scientist, that this is kind of an unsettling image. So the reason why it's unsettling for me, that is because what we are seeing here is that although we've actually reduced the dimensionality of our data, although we are coloring by controls and cases, and each dot here represents sample, of course, we do not really see a clear distinction pattern when it comes to the 2 different groups. So in an ideal scenario, especially considering that we're working with 2 different, categories of people, like patients and healthy people, that is, we would actually expect in an ideal scenario, once again, that we would actually have 2 distinct groups. One which would contain everyone that is a case, and one which contains everyone that is a control, or rather 2 very distinct groups with maybe a few samples here and there, but not this kind of mess that we actually got. And although this is unsettling, and although this is something that we do not really like to see, it's also, in my humble opinion, a very good thing to have, especially over this course, because it actually shows us that just because we have different tools, just because we have different methods, does not mean that they are going to give us the wanted result every single time. So why are we getting this kind of mess right there? There could be multiple different reasons. The first one could be because of the fact that PCA, in particular as an algorithm, is actually linear based, which means, again, that the two vectors that are created are essentially linear combinations of all the features that we start out with. And this can be problematic in a very complex data set, which includes many different nonlinear patterns, because PCA will not be able to capture these patterns correctly and create very good, or rather accurate, representations of the data that we're checking. So this could actually be one of the explanations, or rather the reasons why we're getting this particular result. Another explanation could be the fact that we have a lot of different features, like we have 13 features, and as we've seen before through the violin plots and perhaps through the correlation heat map, not all of them are actually able to help us distinguish between the two conditions of the target variable. So what does that mean for us? It could mean that if I actually move on and perform some sort of feature selection, like if I discard certain features that are not really all that helpful, or if they contain redundant pieces of information, then the final result that I get out of PCA might actually be a lot better. But before moving on with this, we could also try using, nonlinear algorithms, things like UMAP and TSNE. So let's do that as well. So again, UMAP, just for the sake of history, is essentially considered to be an evolution of TSNE, which is a nonlinear algorithm. As you can see right there from the notes that you also have available, it creates a high dimensionality graph to represent the data. And then you basically try to optimize it into a lower dimensionality, like in 2 or 3 dimensions. And the result that we get is this one right there. So this is basically like getting one, unsettling image after the other, because once again, we do not have a clear distinction pattern, between our samples. And it might be scary when we start out with our analysis, because this is something that we do not really want to see. However, it does not mean that we have to panic. It does not mean that we've done something wrong. It does not mean, in other words, just because we see a pattern like this, does not mean that we've actually run into issues when it comes to the other pre-processing steps that we run out. So even though we might have done everything correctly when it comes to pre-processing and converting variables and whatnot, and keeping the balance when it comes to the different categories, we still get chaotic, patterns such as this. Again, the reasons are multiple. Perhaps the data set is so complex that even UMAP is not able to capture the nonlinear, extremely chaotic patterns of, the data set itself. It might be, again, because of the features or some other, kind of problem that we run out that I do not really have in mind right now. But before basically moving on to actually make assumptions and make conclusions, we have to run our third algorithm. And that is, of course, TSNE. So again, the same thing can pretty much be said in the case of TSNE. And to be 100% sure that there is a particular issue with our data set, whether that is because of the features, or rather because of the visualization and dimensionality reduction algorithms that we work with, we can also check out the 3D representations of, our algorithm. So as you can see, PCA is a complete mess, once again, even in 3 dimensions. The same will pretty much go for UMAP. Let's also check this out. Okay. And the same pretty much goes for TSNE. However, there is actually another kind of interpretation that we can give if we take a look, not in TSNE, but if we take a look over here when it comes to this UMAP representation. So as you can probably see here, you can see my cursor, right? So we actually have this little sort of island. If you can see the curve that I'm trying to create, this sort of a circle that I'm doing, which includes all of these samples, right? So it includes both controls and cases, yes, but there is also another thing that we must consider in this particular case, in this particular data set, and that is the fact that we've actually made a simplification from a binary classification problem, from a multi-class classification problem, sorry, to a binary classification one. So what this actually could mean for us is that the reason why these particular samples, as well as the other ones down there, for instance, are actually clustered, very closely together in either the 2 or the 3-dimensional representations of our data through UMAP, for instance, is because control samples could actually be very close to these disease ones, because these are actually patients of type 1, or rather people that do suffer from cardiovascular disease. However, their case is not really all that severe. It could also mean something like this. So and this is another piece of insight here. So if you actually simplify a problem from multi-class to binary, like in our case, and you perform, things like dimensionality reduction, and it does not work, then it could actually mean that simplifying it is not really the way to go. Maybe you should actually go back and actually approach it as a multi-class classification problem. But before we conclude this, before we make this final conclusion when it comes to whether we're going to use the binary or the multi-class classification configuration of our data, we should also check other things like feature selection, for example, right? So after doing all these steps, this is basically the thing that I'm trying to relay here, is that this is going to be the final decision that we're going to make. However, I'm actually getting ahead of myself just to basically tell you why we're doing all this. So what's the reason behind this? So the other thing that we could do, of course, aside from working, other spoilers as well. So the other thing that we could be doing when it comes to our particular data set is actually try to perform binary classification. So we could actually do this by using models from scikit-learn, things like a random forest or a decision tree or what have you, or we could be using PyCarry, as we've seen in the past lecture that we had. And once again, are we going to use PyCarry in order to make a final concrete prediction? The answer to that is no. We are actually going to use it in order to be able to evaluate many different algorithms on our data set and check out how these algorithms actually perform, so that we can get better insights as to the information and the complexity of our data. So in order to do so, again, we have to import our libraries. Again, this is perhaps a bit tiring, but the thing that I'm trying to relay again through all of this is that the particular strategy that we're using when it comes to working with notebooks, at least in our case, when it comes to data science, is pretty much the same across all of them. So we do not really have to change anything aside from the particular task that we're working with. Again, let's cancel that. You see that this is the data set that we have. We've already seen that. In this case, we are actually going to have to set up an experiment like data frame. And then we would also have to specify that our target variable is tag right there. So the experiment is actually being set up as we speak. Okay, this can be a bit of a tedious process, but bear with me. It's going to take a few seconds. And then, of course, the next thing that we would be doing, the next step, would be to basically compare our different models. And there we go. As you can basically see here, this is our experiment. So it's a binary classification one. These many samples are going to be used for training, and these many ones are going to be used for, evaluating or testing our models. So now we can move forward with the comparison, and we're actually going to get a matrix of different metrics, of evaluation metrics, that is, that will actually help us determine which is the best performing of our classifiers. And again, it's going to be a bit of a tedious procedure. We have to wait a bit. But yeah, bear with me. So again, just as a point of clearance or a reminder, if you actually run this piece of code right there, what it's actually doing is that it compares, like 20 something algorithms on our data set. And then out of these 20 something algorithms, it will actually store the best one, or rather the one that actually achieves to have the highest accuracy score. We could also, once again, kind of customize this, and instead of actually using the highest accuracy, to basically use the highest AUC or recall or precision, depending on the metric that we're working with. But right now we're basically working with accuracy, which is the default one for PyCarry, that is. So let's wait a bit further. As you can see, it's actually very close to concluding. So as we wait for it, is there anything you'd like to discuss up until this point? Is there, again, sorry if this is being kind of tiring, but I just want to make sure that everything is 100% clear for everyone. So I'm also going to check the chat. Okay, we're actually very few people today, like 12 people. So, okay, maybe you got tired from, the mumbling that we do, but okay, bear with us. So there we go. This is the result that we get. So the results are also, once again, the best results when it comes to our metrics are highlighted. So you can basically say that we have an accuracy of like 84.6% for logistic regression. And the same interpretation when it comes to best results can be given out for the other metrics that we're working with. But right now, the best model for our particular case is going to be logistic regression. So if we move forward with evaluation, this is the model that we're going to use. And then, of course, we could be using visualizations or evaluations such as this. This is a confusion matrix. We all know what a confusion matrix is up until this point. I mean, we've already seen this. And it's actually very important for, understanding, or rather pitting the ground truth, the true class, against the predictions that the model actually makes. So in this particular case, we have 90 samples in total when it comes to testing logistic regression. And what we've seen is that out of 37 samples have actually been categorized or predicted as one or as patients in our case, and they truly are patients. So this is the number of true positives that we're getting, once again, because these people, yes, they are patients. And the reason why I'm actually saying it like this is because in binary classification problems, we should always have a question in mind. So the particular question that we're having in this scenario is a person suffering from cardiovascular disease or not? So if the answer is yes, then this is how we basically define our true positives. Again, so this actually depends on the questions, but bear with me here. So we also have 35 people that have been classified as controls, and they are controls indeed. So these are the true negatives of our data set. Then we have 5 people right there and have been classified as controls, or rather healthy, when in reality they are patients or they suffer from disease. And this is actually called the false negative. And then we also have the false positive, which means that we have 13 people that have been categorized as being patients when in reality they're healthy. So just as a reminder here, what do we actually want to see in this particular kind of situation in a confusion matrix? Because as we've said before, the confusion matrix is the basis, or it's the main tool that we use in order to calculate all of these different evaluation metrics. So what we would actually want to see is have a very low false negative and false positive values, right? However, if we are actually pressed hard to choose between the two, like which one should be lower, then false, at least when it comes to biomedical problems, then we would actually say that having the lowest false negative value as possible is actually what we would want to do or have. And the reason behind this is because, especially when it comes to clinical decision support systems, which is what we're trying to do in most cases, if you actually have a high false negative value, then this basically means that it basically misclassifies people as, healthy when in reality they're not. And because of the fact that we are actually telling people that this particular tool uses artificial intelligence, so it seems like a very fancy thing for a lot of them, this can actually make them kind of calm. It can actually lead them to believe totally in what we've created, which is not the case, which is not something that we should do, like blindly trust the tools that we're using. And it could actually have grave, consequences for their lives. So what we would actually much rather have is a higher false positive value, because in that particular case, the model will misclassify the people as being, patients when in reality they're healthy, but at least that will actually raise a false alarm. The particular person for which the prediction has been made will probably go on and get a second opinion, and they will be deemed as healthy in the long run. And this is actually a far better thing to have, rather than having people that will not check their, problem through a second opinion, like their condition, and have really serious problems and perhaps even losing their lives in the process. So this is kind of the analytical, or rather the procedural thought that goes on behind these models. But in an ideal scenario, once again, we would actually want to have the lowest possible values, both for false negatives as well as false positives. And then, of course, we can also create, many different other visualizations. As you can see, this is the ROC curve. This is another kind of metric that we're using to evaluate our models. Just as a reminder, the area under the curve is basically the AUC metric that you see right there. So the greater the area, the better our classifier is, because that means that we have a very small false positive rate and a very high true positive rate. We can also have things like these, like a bar plot or a series of bar plots that will actually showcase the actual class in comparison to the predictions that have been made right there. We could have, again, as a reminder, a classification report, but we've already seen that for the two different categories that we have in the data set. We can have curves like precision and recall, and we can actually pit them against each other. So in an ideal scenario, we would actually have this whole entire area covered, but we see that this is not really the case. And then we could also make predictions by using the best model on particular samples of our test set. So if we actually check logistic regression on the 90 samples, what we would actually get is a mean of 80% accuracy. So is this enough as a final result when it comes to binary classification? The answer to that is no, not at all. I mean, in order to deem like a binary classifier as useful or to deploy it as a decision support system, it would actually have to score like 95% of accuracy at the very least. In some cases, it would also have to be more than that. That depends on the data, of course, but this particular case right there, like 80% accuracy, is not really all that enough. So what this means for us, in our case, it could actually mean that we would have to go back and basically fine tune this particular model so that we can actually, test out different hyperparameters and perhaps find the best possible combination of these in order to get going. Or it could also mean that we need to either reduce the amount of features in our data set, like through feature selection. We could also try out different things, like actually giving our algorithms not this particular version of the data set, but rather the normalized or the standardized version of it. So this also plays a very important role. So we could actually be trying out many different things. And in some cases, we could also be making combinations of different parameters just to see which one works best for the particular problem or project that we're working with. Now, the other thing that we could be doing is, of course, clustering. Oh, spoilers. So the difference when it comes to clustering through PyCarry is that it's not really going to run, every single model one right after the other. So you basically have to choose from a specific catalog of models, and you have to choose one model at a time. Or you could also be using a for loop to test many different clustering methods. In this particular case, again, we would have to ignore the target variable. This is something that we would be doing for clustering, of course, because again, we are talking about unsupervised learning. So we are ignoring the ground truth that we have at hand so that we can actually, put samples into particular distinct groups of different, not categories, but basically different teams, so to speak. And then, of course, you can run k-means with two clusters, for example. We could also be using hierarchical clustering or dbScan. But in our case, let's just go with k-means. And then, of course, we can start, plotting our results. Again, the difference when it comes to plots through PyCarry is that they use a library called Plotly for anyone interested. And the reason why we actually might like this is because they are very interactive, as you can see here. I'm moving my cursor and I'm actually checking the PCA coordinates for all of my samples. I'm checking the cluster number and what have you, many different pieces of information. Another nice thing when it comes to Visual Studio Code is that if you actually, work through PyCarry or what other, library you might have, you're also able to download these plots as, PNGs, as, photos pretty much. And that way you can basically create later on or use these pictures or these, figures for a report that you might write in either Microsoft Word or LaTeX so that you can actually relay all of the results and insights that you found through your pipeline with the other colleagues in your team. Okay. So again, we can also employ the help of the ground truth that we have. So you can see here that the coloring corresponds to different clusters. And then we also have ones and zeros, which correspond to the real, values that we have on the target variable. Now, we didn't use ones and zeros here, or rather the tag when it comes to clustering. We're just using it now to visualize our data and get a better example or picture of what goes on. And what we can actually check out here is that although we've created two different clusters, which seem to be, quite distinguishable from each other, actually check the ground truth, we see that both of them contain samples from both categories. So the interpretation is pretty much the same that we would be giving for the dimensionality reduction plots, or rather similar to that. And then, of course, you could also create something like this. You could also create like a three-dimensional representation, which is, as you can actually see here, very, very interactive, right? And you could also be, plotting things like the silhouette score. So this is basically one of the greatest or the most well-established metrics that we are going to be using when it comes to clustering. But let's not delve into it. I mean, we've already discussed this, and we don't want this to be, extremely tiring. And we could also be doing things like these, like actually use dimensionality reduction to check in a two-dimensional space the distance or the theoretical distance between the two clusters, like cluster 0 and 1, as well as the number of samples of each of which. This is not particularly helpful in our case. This is more of a showcase as to the results that we could be using out of PyCarry, because we didn't really see this last time. And then, of course, we could be getting like a bar plot again, which includes the number of samples for our two different distinct clusters. Again, these are clusters. They are not the different categories that we have. Okay, so, and the last thing for today is feature selection. Okay, so we've already talked about dimensionality reduction. We've already talked about pre-processing. about how we can use pictionary for classification or clustering and whatnot. But the thing is, how can we actually perform, feature selection? How can we actually determine, in other words, which are the features of our data set that are extremely helpful when it comes to distinguishing between our different categories, which is healthy and control samples or case samples in our particular case. So there are actually many different approaches, many different algorithms that we could be using. So we could actually be employing a standard statistical test in order to check, for example, like a correlation between our features and, for example, the target variable or the values of the target variable. So this would be called feature filter-based feature selection. The reason why we call it filter-based is because it's the equivalent of actually employing a well-established sort of filter. In our case, it would be a statistical test or a statistical metric in general. Again, things like correlation, for instance. And then there are, either wrapper or embedded algorithms. So wrapper-based methods actually employ specific machine learning models that we choose. They train them iteratively, and then they basically either discard or add features to the data set and they basically check or compare the performance of the algorithm that we chose, either when it comes to adding or removing features. To make things clear, one of them would actually be forward selection. So for example, you are going to get KNN, for example, or what other type of classifier you have. You would actually start with the data set having only one feature, a random feature. It doesn't matter which one it is. We would check the performance of KNN by using this particular feature. We would actually write it down, that is. Then we would add a second one. It could be, again, something random out of the 13 features that we have. We train and test KNN once again. We write down the result. And then comes the question, is this performance that we get with two features better compared to what we got with the first feature that we used? And if the answer is yes, then the second feature will also be kept in the data set. And then we move on until we've used, all the combinations of, the different 13 features in our case that we have in our data. And then there's also backward selection, so which means that you could actually start by employing every single one of your features, all the 13 features that you start out with, or elimination in that case, and basically start removing them and evaluating your algorithm, whichever it might have been, whether it is KNN or support vector machine or what have you. And then there is also a third class of methods, which are called embedded. And the reason why we actually call them embedded is because they are proprietary or specific to or tied, if you prefer, to particular machine learning classifiers. For example, feature importance is a metric or a score that we use, which is readily associated with decision trees or tree-based algorithms, pretty much. And the reason behind this is because if you actually recall from last time, a decision tree actually looks a lot like this, right? So we basically use features, and we use specific values of features, and we use them to create dilemmas of yes or no. So for example, if age is lower than 45, yes or no, and we move on to particular branches of the tree until we go to the final solution, which are called the leaves, or the final prediction that is made by the tree itself. And this is a very basic representation of a decision tree. And the reason why I say this is because in most cases, if not all of them, well, it's not all of them, but in most of them, okay, these trees are actually far deeper than what you see here, which means that we have many different layers of such, questions. And feature importance basically tells us the metrics that we use from such trees. How important is each feature when it comes to actually creating this split and making a good, final accurate prediction? In the case of trees, a good final prediction means that in the leaves or at the end solution, we have samples that only belong to one category. category. So for example, in this particular case, which is the ideal one in this example, we would actually expect to have samples that belong in category high and only that in this particular leaf right there. And the same pretty much applies for low, low, and high right there, and for their corresponding values, that is. Now, decision trees are very nice. We really like them because they're interpretable. However, the problem is that when we're working with very large data sets, very complex data sets, they might not be able to capture the intricate or the complex relations that exist within such data, or the patterns, that is. And that we actually employ the help of ensemble methods. So what does that mean for us? What is an ensemble method? It basically means that instead of using a single classifier in the case of binary classification, we are actually going to be using multiple classifiers. So we could be using many different ones. We could be using a decision tree, a support vector machine, and something different and something else, for example, like a random forest or whatever. And then we're actually going to combine the predictions of these three models in order to get a final consensus prediction. And the reason why we actually do this is because if you combine the strengths of three weak models, weak when it comes to very complex data, then you're going to create a final model which is actually going to be stronger and thus be able to make more, precise, more accurate predictions down the line. So this is the reason why we employ ensemble methods, in order to have more robust, more meaningful, more accurate results. And there are tree-based algorithms, and what that means, tree-based ensemble algorithms, is that instead of using many different classifiers like a decision tree, a support vector machine, and something else entirely like a KNN, for instance, they actually use multiple instances of a decision tree. So they create like 1,000 decision trees, and then they basically proceed to either training them on parallel or one after the other, as you can see here. And what happens is that a consensus, or a final, prediction that takes into account all of the predictions of all the decision trees within the ensemble, is actually created, so that we can have a more objective final, thing to work with. And this particular method right there, where we train models or trees in parallel in an ensemble model, is actually called bagging. Random forest, which I'm sure that most of you will have heard of, is actually working in such a way. And this particular method, where we actually train decision trees, in a sequential manner, one after the other, in order to basically highlight the weaknesses of the previous model to the next one, is called boosting. And gradient boosting, like algorithms like XGBoost, for example, or LightGBM, or what have you, are actually combining this particular method of operation along with a loss function, which means that you are also, they are also obliged, so to speak, to reduce a score which basically tells them how wrong of a prediction they're doing. So you're basically employing two different criteria in order to be able to make, some very good, final predictions. Now, does that mean that these models actually work like ensemble models? Yeah, they do. I mean, this is not just theory right there. These models like XGBoost, CatBoost, LightGBM, gradient boosting trees in general, as well as random forests, are actually some of the best, classic, so to speak, machine learning models that you could be using. They've been dominating Kaggle competitions for a while. And the only models that have actually been able to dethrone them, so to speak, especially when it comes to models like XGBoost, are some artificial neural network architectures, which are, of course, very complex and perhaps difficult to understand. So the thing is that, why do we actually like models such as, XGBoost or CatBoost, these gradient boosting, ensemble tree-based algorithms, right? So we like them because they are very robust when it comes to working with complex data. And we also like them because, you can employ the feature importance criterion, which is, embedded into decision trees. So you basically get kind of the best of both worlds. You get very good performance, and at the same time, you get a certain level of interpretability of what actually matters in our data set. The problem, however, is which of these algorithms are we going to use? And the reason why I'm saying this is because we have three very well-established, gradient boosting tree-based models. Like we have XGBoost, we have CatBoost, and then we also have LightGBM. So which one are we actually going to employ? And why would we actually employ one of which over the other? So the counter question to this is, why not actually use all of them? Why not use the prediction that all of these models will output to us into a final consensus? And this is what we're basically trying to do here when it comes to feature importance. So imagine here that we have our three models. These are our three experts. So XGBoost, for example, CatBoost, and LightGBM, three gradient boosting trees, right? So this is basically the order of features. So K1 is feature number 1, K2 is feature number 2, K3 is feature number 3, for instance. So our different columns in our particular example. And each of these algorithms is actually ranking these features, these particular features, from scores that go from K minus 3, so from 3 minus 1, sorry, so from 2 all the way down to 0. So a higher score in all of these lists indicates a higher level of importance. So expert number 1, which could be XGBoost, for example, will actually give us a list of the features that we have from most to least important. Same goes for the second one, and same goes for the third one. This is a typo right there. Imagine that this is the third one. And what we're actually doing is that we are employing an aggregation method, which is called BORDA, for instance, in this case. And what we're saying is that in order to be able to classify features as the most important, we're not going to take one of these lists on its own. We're actually going to get all three of them, and we're going to aggregate these ranks. So what I basically see here, as you can see, this is simple addition, is that if I add the degree of importance for K1, I get a final value of 6. So this is the most important feature according to all three of the models that I've used. Same goes for K3. This is the second most important one. And then K2 is actually the least important one. But this time, instead of simply employing XGBoost or CatBoost or what have you individually, I'm actually combining, the predictions or the opinions of these three very well-established and robust models in order to make things even more robust, even more objective when it comes to producing a final evaluation, again, when it comes to what's important and what's not, as far as features go, as far as feature selection. And, just to put things a bit into context, this particular algorithm is something that we've actually employed ourselves in our laboratory, and we've actually also made a paper out of it in IEEE Big Data back in 2022. So the reason why I'm saying this is because this particular algorithm has been working very well, not only when it comes to this particular, simple clinical data set. We've also employed it to high dimensional big data, more specifically single cell RNA sequencing data sets, where we actually have like 25,000 genes as features. And through this methodology, we were able to identify from 30,000 features a subset of like 700, which were the most important ones. They might seem quite a lot still, and they are, that's true. But compared to having 25 to 30,000 features to begin with, I'd say that 750 features is actually a lot less of a number to work with. And if we do not want to discard features from our particular data set, we could also be getting, a representation such as this. So we basically have all of our features in the y-axis, and the x-axis showcases the importance or the rank that we obtained through our, aggregation scheme, which is this one right there. So what can be seen here, for example, is that tall, CA, and CP, for instance, are the top three most important features for our particular case. And this actually comes back to the correlation heat map that we've been using, as well as the violin plot, because if we go on and combine all of the results that we got, as well as the box plot with the statistical significance, because if we combine all of these, we are actually going to say at the end of the day that we had indications, statistical indications, that these actually have a difference between cases and controls. And we can also see this in an algorithmic manner, through feature importance by employing three very well-established, machine learning models. So at the end of the day, how can we actually proceed as next steps for this particular problem? We would actually go ahead and pick the top 4 or the top 5 features that we get out of this procedure. And instead of using all 13 of them, actually use these in order to perform, again, dimensionality reduction or classification or even clustering. So there are a lot of different things that we could be doing, but let's leave it at that. So having said all these, this was basically the things that I actually wanted to present to you today. So now I know that it was actually, I was very talkative, so to speak. I actually might have been a bit tiring. So is there anything you'd like to discuss up until this point right now? Was everything understandable? Is there anything you'd like to discuss? So, feedback would be appreciated, even if it's negative. I mean, I always appreciate it. Yeah, of course. And
thank you very much. I have it was very interesting, and I think it is the most important topic in this course to deal with the health and improve this kind of topics. My question is basically theoretically that how does it work in the real life? How can avoid the problem if we don't know some kind of aspect. Let me give an example. It may be easier to understand my problem. That I mean, 100 years ago, nobody knew why is the baby mortality so high, and Semmelweis find out, and before this, nobody know about this infection. So if I have a very large database and I calculated that, will the module and the algorithm find out that out of the scope is the reason what I'm looking for, or how is it work?
okay, so if I actually got this correctly, the question is, how can we actually search for specific patterns if we don't really know what we're looking for, right?
Yes, exactly. Thank you very
Okay,
much.
so this is actually a very interesting thing, because in most cases, when it comes to biomedical problems, we might not exactly know what we are looking for, or we might expect something, we might make hypotheses, but the end result will actually be, in most cases, actually quite different from what we expect. And the reason why I say this is because, as you've said correctly, like 100 years ago, we did not know, for example, why baby mortality was actually elevated in some cases, right? So the problem back then, however, I'd say, is that we didn't have a lot of, good documented cases. We didn't have, large data sets for particular types of disease. And at the same time, we didn't have the computing power in order to use algorithms such as the ones that we're using now. And this is basically the whole entire kind of reason why we are occupying ourselves with, artificial intelligence and machine learning. The reason why I say this is because it's basically kind of backwards in the way we would actually think. Like in most scenarios, you have input, you have some specific insights or pieces of information that you observe. And then you also have a certain set of steps that you can follow so that you can actually move on to a final result, right? So the goal of machine learning is not to do that. In machine learning, you have your input, or rather, some particular measurements that you get depending on the problem that you have. And you also have the final output. For example, a specific phenotype, like whether a person actually suffers from disease or not, whether babies are dying or not in a more serious kind of scenario. And the beauty of it is that by employing the methods that we use, and many more than these, like even if we employ neural networks and whatnot, we are able to use our input and our output in order to basically create the set of steps that are required to go from the input to the output. So this is the first thing. This is actually one of the things that is actually very important to clear out. The second one is that in most cases, at least when it comes to biomedical problems, there are specific types of arguments, or rather narratives, that will have to be confirmed later on. And in a lot of cases, if the narrative is not confirmed, which means that we do not really know exactly what we're working with, we basically let our data guide us. So we perform our certain analyses, and for example, in gene expression data, for example, in cancer studies, which is something that we do here in the laboratory, we actually check specific sets of genes that have also been reported in bibliography. And if we find something new, something that is not reported, one of the things that we would actually proceed with doing is actually trying to check through enrichment methods, for example, is how these genes that we found actually correlate with cancer or other similar types of disease. So even though we do not really have the full picture, we're actually trying to create it by basically puzzling, little pieces together and little insights that we get that are data driven. Now, does that mean that everything has to be data driven and not have a clear, hypothesis, a clear narrative in mind? I'd actually say that at the end of the day, it should actually be like a combination of these two. Like, have a clear narrative, actually have a very specific question when it comes to, again, biomedical problems, that is, and then constantly check whether the assumption that you've made, the hypothesis, actually holds water, not only in terms of machine learning algorithms and other computational methods, but also when it comes to wet labs. So aside, again, I'm using cancer examples, like cancer types of disease, but okay. So in cancer studies, even if we actually report a certain set of genes, and a biologist or a doctor actually confirms that what we've actually highlighted makes sense, the very next thing that they would be doing is actually run a wet lab, actually, which means that they would actually try to isolate, pieces of tissue and basically confirm everything that we found computationally through some sort of their own, medical or biological experiment. So the thing that I'm trying to say, this is kind of a long answer, and sorry for that, but at the end of the day, even though we might not have the clearest of pictures for specific problems, the data actually help us paint these pictures along the way. And this is actually, I'd say, the biggest promise of machine learning. So the fact that you do not necessarily need to have a specific set of steps that might have also been wrong at some point in order to proceed to a final result. You do have the final output, the input, and you basically use this in order to guide yourself and basically understand specific mechanisms, perhaps in a better way than what we would have done with some traditional methods. So I don't know if that answers the question. I'm sorry, but I got ahead of myself.
Well, thank you very much for the great explanation. It was very, very interesting. Thank you.
Okay, you're welcome. So,
and sorry, let me have one more very short
yeah,
question.
of course.
Can of course this model calculate also with the timeline? I mean, for example, back to the cancer, as I see, there is even more cancer problem in Europe. and how can the model calculate with the timeline? In Manuri, there is a lot of very young people with cancer.
Mhm.
And I mean, 20 years ago, it was not really common health problem.
Okay, so the question is how we can actually understand the particular reasons for the disease. Is that what you're asking?
Yes, exactly.
Okay, so in most cases, this is actually done through assumptions that are made by doctors and biologists. Like the first thing that happens, especially in cancer studies, depending on the type of cancer that we are studying, is that there are some specific kind of molecular mechanisms that exist. We do not really know how they work, but we know that they do exist. And what we're actually trying to do by analyzing, data like gene expression data and combining them with clinical data and demographics and whatnot, is to be able to clear out these particular molecular mechanisms. And the reason why this becomes specific down to the level of molecules is because if we are able to understand the molecular, again, basis of a specific disease, of a complex disease, such as cancer, or different types of cancer, that is, then we might be able in the future not only to create, decision support systems, but also give doctors, chemists, and biologists the ability or the input that is required for them to create, potential new types of therapy. So the first goal out of all of these types of research is not necessarily only to produce, different types of drugs and treatments, but to also be able to understand the mechanisms that actually underlie the disease in a better way. Because, for example, in cancer studies, for instance, the most well-established kind of treatment, aside from surgery, is chemotherapies. Like, okay, we already know that. However, in recent years, because of the fact that we understand molecular mechanisms better because of computational studies, there have also been some other kinds of different types of treatments, like immunotherapies, for example, or checkpoint inhibitors and whatnot. So many different new experimental types of treatments or therapies or drugs, whatever you want to call them, that are not based on chemo. So then the reason behind the result, this is actually the result of actually getting a better understanding of how some particular known molecular mechanisms actually work. Well, I'm calling them known because we know that, again, we know that they exist, we are aware of them, but we do not fully understand the way they basically, evolve and move on down the line. So the main idea, the main thing that we're trying to do is this: basically understand why some specific types of cancer, for example, actually go down the way they do, and what makes specific types of aggressive cancer different when it comes to, molecularly speaking, to less aggressive types of cancer. And what has actually been seen so far, for example, in prostate cancer, which is the research that we're doing, is that although the focus of most laboratories actually happens in very aggressive types of prostate cancer, it should also be noted that less aggressive types of prostate cancer, once again, are actually quite risky, because although they evolve or they move forward or they develop, if you prefer, in slower rates, they are actually more resistant, far more resistant in a lot of cases, to many different types of chemo or even other types of drugs. So even though they do not move on or develop as quickly, they're still a very dangerous problem to, go with. So again, the main goal is to, especially, for example, in Europe, as well as the United States, is to be able to understand, again, the molecular basis of, complex disease in particular. Not only when it comes to cancer, but also when it comes to other things like neurodegenerative types of disease, like Alzheimer's, for example, or other different types of dementia. Again, kind of a long answer, kind of a tiring answer, perhaps, but yeah.
Thank you very much. Thank you.
You're welcome. You're
All
welcome.
right.
So Okay, so is there any other questions? I mean, from anyone else? Oh, thank you, John. Okay, so if there are no other questions, I am very glad that you were all able to be here with me. Thank you very much for your attention. And I'll see you for our last lecture, which is going to be at the 17th of the month. So um, we are going to have a short break, and you're going to continue the lecture, the other 2 hour session with a different lecturer, a different instructor. So have a good one, everyone. Thank you very much for being here.